Hello students, welcome to Engineers Academy. Do hit the subscribe button if you are here for the first time. Now in this video we are going to solve these two problems which are related to each other. So problem 359 says that the frame ACD is hinged at A and D and is supported by a cable that passes through a ring at B and is attached to hook at G and H. Knowing that the tension in the cable is 450 Newton, determine the moment about the diagonal AD of the force exerted on the frame by portion BH of the cable. So we are given this frame ACD which is supported at A and D and by these two by this rope which is passing through this ring attached to this G and H. Now we are asked to find the tension, we are asked to find the moment about this AD line of the portion of the tension from B to H, which has a magnitude of 450 Newton. So what I am going to do is that I am going to remove this portion of the rope because we are required to find the moment of only this part of the cable, or we can say this part of the tension in the cable. So let me erase B to H part of the rope. So this is not, for this particular problem we are not going to consider this part of the cable or the tension in this part of the cable. So we are only interested in the tension which is acting from B to H, which has a magnitude of 450 Newton. So let me write the magnitude of this tension. So this magnitude of the tension is 450 Newton from B to H. Now what we are going to do is that you guys can do this in two different methods. The first method is you guys find the moment of this tension T about any point on this AD line. So that will be the moment about that particular point. So let's say if you want to find the moment about this point A, which this point A lies on this AD line, so we will find MA. So MA will be equal to R cross that tension T, and this R will be a vector which will start from B and will end on A if you want to find the moment about point A. Or we can find the moment about point D. So if we find the moment about point D, that will be R of D relative to B cross product with that tension T. So that will give us the moment about D. Once we find the moment about A or D, then we will take the dot product of that particular moment with the unit vector for which will be acting from A to D. So we can say that I can write that formula here for you guys. That's the first method, but I'm going to use the second method, which is the scalar triple product. So we can say that we can find the moment about A by using this cross product method, which will be R of B relative to A cross product with that tension vector. Or we can find the moment about point D, and that will be R of B relative to D cross product with that tension T. So this will give us the vector representation of the moment about point A or D. And then once finding the moment about A, and in order to find the moment about AD, if you want to find the magnitude of the moment about AD, we will take the dot product of one of these with the unit vector from A to D. So we can write that the magnitude of the moment about that diagonal AD will be equal to MA vector dot product with the unit vector from A to D. Or we can say that this magnitude will be equal to moment about D cross product with the unit vector along AD. So this is the first method you guys can do and find the solution and find the moment of this particular tension about this line AD. And the second method is using the scalar triple product. So this is in the same method, but it is using the determinant of a matrix of a 3 cross 3 matrix. So this is the the easiest method. This is the easiest method as well, but this is the, you guys can see, this is the method which makes our life easier, and we can just find the determinant and will give us the solution. So this is the scalar triple product. You guys can see that this is R of B relative to A cross T, which is equal to MA. So this is that MA, and then taking the dot product with AD. So this is the same method, you guys can see, but in this is known as the scalar triple product. In scalar triple product, we write the unit vector before the cross product, before the moment. So we take the dot product of the unit vector with MA or MB, and which will give us the magnitude of the moment about that line AD. So now if I write this equation, which is MAD, and this is the position vector along, this is the unit vector along AD, since we want to find the moment about this particular line, and then this is the moment of that tension T about point A. So R of B relative to A is this vector, and then we find the Cartesian vector representation of that tension T. So now we will find these one by one. So we will find the unit vector from A to D. Now the unit vector from A to D is the position vector from A to D divided by its magnitude. Now the position vector from A to D is this vector. So we must find this position vector from A to D. So in order to write the position vector from A to D, we must start from A and we'll try to reach that point D while traveling along the X, Y, and Z. So from A, we need to travel 0.75 meters in the negative Z. This is the positive Z. We are moving in the opposite direction. So 0.75 in the negative Z means 0.75 in the negative K. So we will reach the origin, and from the origin we need to travel 0.5 plus 0.5, which is 1 meters in the positive X. So 1 meters in the positive I. And since we have reached point D without traveling in the Y direction, so this means that the J component is 0. So this is the position vector from A to D. Now finding the magnitude of this position vector will be 1 square plus 0 square plus 0.75 square under the square root, which gives us 1.25 meters. Now the direct distance between point A and D is 1.25 meters. Now in order to find the unit vector, we have to divide each of these components by this magnitude. So if we divide each of these components by magnitude, we will get the unit vector from A to D, 0.8i plus 0j minus 0.6k, and this is unitless because these are in meters and the magnitude is in meters, and meter will cancel out, and the unit vector is always unitless. Now the second thing we need to find is the position vector of B relative to A, which is this vector. So again, to write the position vector of B relative to A, we must start from A and we'll try to reach that point B while traveling along the X, Y, and Z. So in order to reach this point B, we need to travel directly in the positive X direction, 0.5 meters. So 0.5 meters in the positive I, 0 units along the y-axis and 0 meters along the x-axis, because we only need to travel in the x in order to reach that point B. So the position vector of B relative to A is 0.5i plus 0j plus 0k, and the units of this is in meters. Remember, this is in meter. And the third term which we need to find is to find the Cartesian vector representation of that tension T, which is acting from B to H. So that Cartesian vector T will be equal to 450 times the unit vector which is acting from B to H, and 450, and the unit vector from B to H is the position vector from B to H divided by the magnitude of that position vector. So now we have to find the position vector from B to H. So in order to find the position vector from B to H, again we will start from B and we'll try to reach that point H while traveling along the X, Y, and Z axis respectively. So from B we need to travel 0.5 meters in the negative X, so minus 0.5 in the negative I, or we can say 0.5 in the negative I. We will reach here. Then from here we need to travel 0.75 in the negative Z, or we can say 0.75 in the negative K, so 0.5 in the negative K. Then we need to travel this distance, this much distance in the positive I, so 0.875 in the positive I, we will reach somewhere here, and then from here we need to travel 0.75 meters in the positive j. So 0.5 meters in the positive j. So we have traveled this 0.5 meters in the negative x, 0.75 in the negative z, 0.875 in the positive x, and then from here we traveled 0.75 in the positive j. So we can add both of these I terms. So when we add both of these, we will get 0.375 in the positive I. So this means that the distance between point B and H along the x direction is 0.375 h. So 0.375 I plus 0.75 j minus 0.75 k is the position vector from B to H. And again, if we find the magnitude of this will be 0.375. The magnitude will be 0.375 square plus 0.75 square plus 0.75 square under the square root, and that gives us 1.125 meters. So this is in meters and this is in meters. This cancels out. So this is the unit vector. Now, if we divide 450 by 1.125, that gives us 400. And 400 multiplied by all these components gives us the Cartesian vector representation of that tension T from B to H, which will be 150I plus 300J minus 300K, and the units are in newtons. Now, once we find these three, this unit vector from A to D, the position vector of B relative to A, and the Cartesian vector representation of that T, then we need to write them in a determinant of a matrix of a 3 cross 3. So this is the first row represents the unit vector from A to D, and this will each of this element of the matrix represents the component of those unit vectors. So this is 0.80 and minus 0.6, 0.80 minus 0.6. This is the R of B relative to A, the second element in that equation, and the components of that. So this is 0.50 and 0, 0.50 and 0, and the last term is the components of that T vector. So 150 plus 300 minus 300, 150 plus 300 minus 300. Now, while finding the determinant of a matrix, we always select that particular row which has more number of zeros. So in this second row we have 2 zeros, so that will make our life easier, and we will try to use this element of the matrix of the determinant to find the magnitude of the moment about that diagonal AD. So while finding the determinant, we must write minus 1 to the power, since this 0.5 is in second row and first column, so minus 1 to the power of rows plus column, so 2 plus 1, then 0.5, then hiding this row and this column, so 0 into minus 300 is 0, and minus into minus 0.6 into 300, so minus into minus 0.6 into 300 gives us 180, and this minus 1 to the power 3 is minus, so minus into 0.5 into 180 gives us minus 90 Newton meter. So this is the magnitude of the moment about that diagonal AD, and the negative sign tells us that the moment is in the opposite direction of the unit vector that we have selected. So we can select the unit vector from D to A as well. If we could have selected the unit vector from D to A, then we would have got this as positive sign. But since we have selected the unit vector from A to D, we got the negative sign. The negative sign tells us that the moment is in the opposite direction of the unit vector. So this means that if the moment of this tension T is in the opposite direction of that unit vector, so this means that this is going to be the moment AD. So this will be the direction, because if we curl our right hand fingers in this direction, so the thumb will point out in the opposite direction of AD. So the moment AD has a magnitude of 90 Newton meter, and it is in the opposite direction of the unit vector which we have selected from A to D. So the negative sign tells us the direction. So minus 90 Newton meter is the moment, the magnitude of the moment of that tension T about that line AD. Now this problem says that Problem 368 says that in problem 359, determine the perpendicular distance between the portion BH of the cable and the diagonal AD. We are asked to find the perpendicular distance between this BH line and this AD line, which could be some line like this, which is going to make 90-degree with that AD line. So for this particular method, for this solution, we must resolve this t vector into two components, because we can find that perpendicular distance between this line BH and this AD by using the scalar method, by using the scalar definition of the moment. And the scalar definition of the moment is always this is the perpendicular distance, or we can say the distance multiplied by the force, right? As we know that the scalar definition of the moment is always equal to d times f, and as we know that the moment is always r cross f, and we can say that uh, we can say rf sine of theta, and r sine of theta is the perpendicular distance. So we can say that this is d perpendicular multiplied by that force F, which is going to produce the moment about a given axis. Now, as you guys can see that since this tension T is going to produce the moment about AD, but if we resolve this tension T into two components, one component along this AD line and one component perpendicular to this AD. So the component which is parallel to this AD is not going to produce the moment about this AD. So, and the component which is perpendicular to this AD is going to produce that moment of 90 Newton meter about this AD line. So that will help us, because this tension T is having three components, as we have found this by using the by finding the Cartesian vector representation. As we know that this tension T will have 150 Newton component in the positive x, 300 Newton in the positive y, and 300 Newton in the negative k. These are the x, y, and z components. But in order to find the perpendicular distance between this BH, which is the line of action of this T, and this AD, we need to resolve this tension T into two components, one of which is parallel to this AD and the other perpendicular to that AD. So what that will do is that will give us the perpendicular distance according to the definition of that moment, scalar definition of that moment. So once we find the parallel component, we can always use the Pythagoras theorem, because these are the rectangular components. This component is parallel to this AD and this component is perpendicular to that AD. So once we find this, we can use this Pythagoras theorem to find the magnitude of T parallel, and putting that magnitude in this equation will give us the perpendicular distance which is required from BH, between BH and that AD line. Now, how to find the component of this T parallel to this AD? So that's very easy. We can take the dot product of this T vector with the unit vector along AD. So that will give us T parallel. So T parallel is equal to T times the unit vector from A to D. So this is that T vector that we have already determined, the Cartesian vector representation of that tension T, which is acting from B to H, times the dot product with the unit vector from A to D. So if we take the dot product, we will 150 multiplied by 0.8 I dot I, and if we multiply 150i with this, so that will become 0, and 150i into this will be I dot k is always equals to 0. So while taking the dot product, we only multiply I with I, j with j, and k with k. So 150 into 0.8 I dot I is 1, 300 into 0, and minus 300 into minus 0.6. So once we find this is equal to 120, this is equal to minus into minus is plus 180, 120 plus 180 is 300 unit. Now the component of this tension T parallel to this AD has a magnitude of 300 Newton. And we know by the Pythagoras theorem that the magnitude, this t square, which is the hypotenuse, this t magnitude square is equal to t parallel square plus t perpendicular square. We want to find t perpendicular. So rearranging this equation, we can write this on this side. So we can bring this to the other side. So we will have t perpendicular square equals to t square minus t parallel square. Then taking the square root, we will have the equation like this. Now we know the magnitude of that tension T, which is 450 given in the problem statement. So 450 square minus 300 square we have just determined by taking the dot product of that T with the unit vector from A to D. So once we put these, we get the magnitude of the component which is parallel to that AD line. So this is 335.41 Newton. So once we find this perpendicular component, now as you guys can see, we can draw this T perpendicular here as well, and we can draw that T parallel here as well. So if I draw that T perpendicular here, so this is going to produce the moment about that AD, and if we multiply this with that distance, so that will give us the perpendicular distance between this BH and that AD according to the scalar definition of the moment. So D perpendicular distance multiplied by T parallel is equal to 90. We are going to take only the magnitude, so 90 Newton meter, and D will be equal to 90 divided by that perpendicular component. So 90 divided by T perpendicular. So 90 divided by 335.41 Newton gives us 0.268 meters. So the perpendicular distance between this line BH along which that tension T is acting and that AD, that diagonal, is 0.268 meters. So this is the solution of this particular problem. I hope this will help you in your learning. Do subscribe Engineers Academy for the solution of such more problems from Vector Mechanics for Engineers by Baer and Jhonston.